Okay, here we are again. This will be the last section that we will do in Chapter 7. After this, we'll be working in Chapter 8. Let's see what we can do with it. Okay. Determine if a complex number solves an equation. Find an equation that has certain numbers, complex numbers, as solutions. So in this one, we'll actually be going backwards. Usually we have the equation, and we have to figure out what the solutions are. In this case, we'll have the solution, and from that, well, solutions, from that we'll figure out what the equation is. Solve first-degree equations with complex numbers as solutions. We know what this means. This means that the variable is to the first degree, whichever it is. Verify and find square roots of complex numbers. Square roots of complex numbers, that sounds interesting. So more problems involving complex numbers. Let's see what we've got in front of us here today. We've got 3 slides and then another 3 slides. Okay, we can get through that. Just a warm-up here. Solve for x and y. These look so familiar to the ones we did in the last lesson. Remember what that was? The real components must be equal to each other, and the imaginary components must be equal to each other. So we end up with 4 equals 2x, and then 5y is equal to 15i. This one, when we solve it, it's supposed to be an x, will be x equals 2. Agree? This one will be y equals 15i divided by 5i. And that will be equal to, the I over I is 1, 15 over 5 is 3. So we've got x equals 2, y equals 3. Multiply these together. Of course, we're going to do first, which is 15. And we're going to do the outside, another term, and that's going to be positive. Positive 5 times positive 4, 20i. Then we're going to do the inside, and that's also going to be positive, the 6i. And finally, the last ones, and that's going to be 8. Watch this, we got I squared. All right, I squared is the same as, well, I squared is a negative 1 times a positive 8 will give us a negative 8. So negative 8 and a positive 15 will be 7 for our real component. And then we're going to combine these like terms to give us a positive 26i. Okay? Finally, we're going to divide. This will be a little trickier, won't it? Let me move this down a little bit just so we can see it better. This will be a little tricky. We need to rationalize our denominator. We'll get ready here with some parentheses. Anytime I'm trying to rationalize a denominator that has either a square root or I in it, I'm going to use, I'm listening, yes, conjugates. So this will be 2i, and instead of taking the difference, we're doing the sum. 2i. Let's do the denominator first. Because we've got conjugates, we don't have to worry about middle terms. So it'll be 2 times 2, or 4, minus I squared. Then we'll have this one. We're going to have to do the whole thing, aren't we? We're going to do the first, which will be 2. The outside, which will be plus 1i. I'll just write plus I. Then we'll do the inside, which is a negative and a positive, so that'll be a negative 4i. And then the last, a negative and a positive 1 will give us a negative 2, and it'll be I squared. Well, I certainly didn't draw this fraction line long enough, did I? We've got two situations, one in the numerator and one in the denominator, where we're looking at I squared. Let's deal with the denominator first. A negative I squared is the same as negative 1, which will be a positive 1. When we add that to 4, we get 5. Over here, we've got a negative 2 times I squared, which is the same as negative 2 times negative 1, or a positive 2. A positive 2, and over here we also have a positive 2, will give us a positive 4. For the imaginary portion of this complex number, we've got a positive 1 and a negative 4. We add those together, we're going to have a negative 3i. So when we divide this, we get this. Well, I think we're ready to move forward. That was just a little review for us, stuff we've done before. How do you determine if you have the solution of an equation? Now, this A stands for any real number, and this part here stands for any imaginary number. B could, of course, be negative. It could be 0, as could be A. Let's determine whether or not this complex number is a solution of this equation. So what we're wondering is, does x equal 2 plus I? We've got x in two places here. So we're going to take those two places and we're going to replace them with parentheses. Now notice there's a lot of space left. Why? Because I have to fit a binomial in where I used to have an x. So it was x squared minus 4x, only I'm going to see if I put in 2 plus I, if it turns out to be true that it equals 0. Let's try it. 2 plus I, 2 plus I. So there's my setup. Now I need to go ahead and do the operation. 2 plus I squared is going to be, you can take a little time with this and make sure that I'm doing it right. You might have to pause. 4i plus I squared. I know it will make a trinomial, and this is what the trinomial will be. In this case, I'm going to take a negative 4 and distribute it to the 2, which will give me a negative 8. Negative 4 distributed to I will give us a negative 4i plus 5 outside the parentheses. This is the same as a negative 1, isn't it? So I've got a positive 4. I'm just going to cross it out because I'm paying attention to it. And I subtract 1, a negative 1. That'll give me a positive 3. And then I'm going to subtract 8. So I had negative 3, I subtract 8, negative 11. And then I add 5. So what have I got for my real number? 0. Wow, that's great. And then I've got plus 4i and negative 4i. Well, that certainly does equal 0. So I would say, since this equation remains true when I put in 2 plus I for its solution, that the answer to this question is yes. It is a solution for that equation. Find the equation having this and this as its solutions. What's that telling me? That's telling me that x is equal to that, and x is also equal to that. I'm going to have to go backwards with this zero product property. Do you remember that zero product property? I'm going to start with x equals 1 plus 2i. I know I'm also going to have to do x equals 1 minus 2i. Now in the zero product property, remember I had many equations at some point and they were equal to 0? Well, I want to have the same thing again, so I'm going to say x, and I'm going to subtract 1 from both sides, and I'm going to subtract 2i from both sides equals 0. And over here, x, subtract the 1 from both sides, add 2i to both sides, and now I'll have that mini equation equal to 0. Our rule with the zero product property was that if we had two factors that when they're multiplied together equals 0, then either one of those factors must be equal to 0. So I'm going to set these up now as factors. You can see we're going backwards to the logic we used to use because we're starting at the end point where we have solutions given to us and we want to find out what the equation is. Yikes, that is a very complicated looking equation. Well, I'm going to write it up here. That's what this was all set up for. X minus 1 minus, that minus looked like a minus, 2i, and x minus 1 plus 2i. I want you to stare at this for a moment. There's something which I am very fond of. Conjugates, right? We could see this as conjugates if we considered that first binomial as just the first term, and then the term on the end as the second term. What do you think? Does that kind of look like conjugates to you? Conjugates are when you have the same first term, and this, I'm asking you to consider a binomial as your first term. Right here, that's your first term in both of these. Second term's the same. The only difference between them is one is a difference and the other is a sum. So we've got conjugates. When I multiply, which is what's happening here, just getting a little too busy looking, I'm multiplying one conjugate times its other, right? what happens? I don't have to worry about a middle term. Given how complicated this all looks, that seems to me like a really good thing. So I'm going to multiply the first together, and that will give me x minus 1 squared. I'll have to do more with it in just a moment. And I'm going to multiply the last together, and that'll give me a negative 4i squared equals 0. This is a binomial squared. You probably remember the pattern. If you don't, you can FOIL it. The I squared is equal to a negative 1. Negative 1 times a negative 4. I'm actually going to have a positive 4 here. These are like terms, so I should combine them, giving me x squared minus 2x plus 5 equals 0. Voila! There is the equation which has for its solutions 1 plus 2i and 1 minus 2i. Isn't that cool? We can know the given solutions and then work backwards to find out what the equation is. We're going to talk about the fundamental theorem of algebra later on. We'll get that in chapter 11. So that's coming up in the future. This is basically what it says, that the degree of a polynomial equation, so if I had, well, let's go backwards here a moment. This one, x squared minus 2x plus 5. X squared minus 2x plus 5 equals 0. We'll use this as our example. What degree is this polynomial equation? You look at the highest power that you have. That's 2. So you're degree 2, and it will have 2 solutions. It is true that a polynomial of any degree will have the same number of solutions as its degree. Well, you might be thinking of something like this. Let's see, x squared plus 2x plus 1 equals 0. If we factor this, x plus 1 squared equals 0, we end up with x equals negative 1. And that certainly looks like we had a degree 2, but we didn't get 2 solutions. But the truth is, we actually had 2 instances of x equaling negative 1. So when we say that a polynomial equation will have the same number of solutions as its degree, we are considering redundant solutions like we had in this second example down here. We're considering redundant solution and complex number solutions. Earlier in our studies, we didn't consider complex number solutions. We only looked for real number solutions. So we have matured a bit in our mathematical understanding. If a polynomial equation is of degree n, must it have n linear factors? And the answer is yes. It's not always easy to get to them, but it will have n linear factors. If you have n solutions, you will have the same number of factors. And so isn't that tidy? No wonder they call it the fundamental theorem of algebra. Let's try solving this one. What do we need to do when we're solving? Now, the first thing you're probably thinking of when you see this is, oh, I can distribute. Whoa, don't do that. You really want to have x all by itself. True? That's what we're trying to do. We're trying to find, what does x equal? It's already been factored out for us, so we don't want to go backwards. What we do want to do is get this coefficient. Isn't that a fancy coefficient? We want to get that out of the way. Right now, x is being multiplied by this binomial. This is actually a complex number. So if it's being multiplied by it, we're going to do the opposite operation, divide by. We'll do that to both sides. And this over this is the same as 1. So here's my answer. Oh, I don't like it too much, though. What do you suppose I don't like about it? That's right. We have an irrational denominator. Worse than irrational, actually. It's a complex number. How can we get that out of there? You know this so well, don't you? I can hear you saying that from here. Conjugates. 3, 4i. And of course we do the same thing to the numerator. And instead of using a sum for conjugates, we use a difference. It is exactly the fact that they have different signs that causes the inside and the outside to cancel each other out. So all we have to worry about is, yeah, I'm listening, the first and the last. So that'll be 9 minus 16i squared. Boy, haven't we seen this one before? Then up here I do have to FOIL the whole thing. I have to do inside and outside. For my first I get a 3. And then for my outside I get a negative 4i. For my inside I get a positive 3i. And for the last, a negative 4i squared. And all of this will be equal to, what's in my denominator here? We can ignore this. It's not that it's not correct, it's just I don't want you to be distracted by it. We'll have 25 down here. And up here we've got a negative 4i and a positive 3i to give us a negative I. This is interesting. I squared is negative 1. Negative 1 times negative 4 will give us a positive 4. Positive 4 and 3 gives me 7. Positive 7 and negative I. So that's what x is equal to right there. Here's an interesting one. Show that x minus this times x minus its conjugate, oh, I like that, is the way you would factor this trinomial. Wow, so we are going to have a complex number as part of our factoring. I know, but I'm going to stop for a moment here because I want you to recognize something. That this factor, x minus this complex number, is equivalent to, if we had an equation, which we are setting up here, is equivalent to saying that that's the solution. And we also have another factor, and the solution that points to is this. Notice that when we go from x as the solution of x, the value of x from an equation, when we put it into a factor, we are going to be subtracting that solution. That's what happened here. We're subtracting those two solutions. So first, when I'm looking at this, I have these associated with each other, the 2 and the 3i, but because of conjugates and how helpful they are, I want you to reassociate these in a little bit different way. To think of the fact that x minus 2 is in this factor and x minus 2 is here, so we can consider this as conjugates. And when we go to multiply this together, if we have conjugates, here's a difference, here's a sum, we can ignore the middle term, allowing me to say x minus 2 squared, and then negative 9i squared equals 0. And we're going to prove that this is a good factoring by showing that this is in fact equal to 0. What? Is it really? I don't think so. Let's see what happens here. X squared minus 4x plus 4, and then we'll have plus 9 equals 0. So x squared minus 4x plus 13 equals 0. It's true. Look, there it is. It's a match. Hallelujah. That's great. We did prove it. Yes. Okay. Every non-zero complex number, well, we know what that means. We've looked at complex numbers that did have 0 in them, has 2 square roots. There should be 2 d's in this thing. They are additive inverses of each other. 0 has 1 square root. Okay. Find the square roots of 16. Okay, well, we can think of that as 16 plus 0i, right? And that would be, if we want to find the square root, square roots, we're going to find plus and minus square roots of that. So $16 oh, don't forget your plus and minus. There it is. Plus or minus the square root of, oh, I don't want to write square root again. Not getting anywhere. Plus or minus plus or minus. What is the square root of 16? 4. Show that 3i is a square root of this. Wow, looks funny. All right, show that it's the square root of that. Find the other root. All right, so how could we do that? Well, we could divide. Let's go back up here and think about this one. If we've got, back up here. If we've got a plus 4 and we square it, that will be equal to 16. So that's proof that that was a good square root. And if we have a negative 4 and we square it, that is also going to be 16. So that's my way of verifying that, in fact, those two are square roots. We should do the same thing here. So if I take 3 minus I and I square it, what I'm expecting to get, if it is in fact the square root of this, is 8 minus 6i. Let's see what happens. This will square, that'll give me 9. I will have a middle term. It'll be negative 3i twice, or negative 6i. And then I'll have a positive I squared. And when I realize that this is the same as a negative 1, I'll have 8 minus 6i. Now, if for some reason you didn't follow that, just go back and do 3 minus I times 3 minus I. Do it a little more slowly with FOIL, and you will get this. Now find the other root. Find the other root. Oh. Well, would the other root be the negative version of that? I could try that. Let's see what happens. So that would be a negative 3 plus I. Let's see if that will work. If I square that, will I get this? We'll see. This would be a 9, and I'd still have a negative 6i here, and this would be a positive I squared. Oh, yes, indeed, it's exactly the same. How nice. Beautiful. And that's it. See you in class.